Well, let us discuss the eddy current, which is one of the important application of Faraday's law of electromagnetic induction. It is also called as focal current, as because focal is the first to identify the presence of such radial current. And how can you define this eddy current? It can be defined as the radial current induced in a thick conductor due to changing magnetic field, as shown in the figure. That means, how can you change the magnetic field? You can change the magnetic field by either moving in or out the thick conductor within a fixed magnetic field. Or the other way is that by keeping the thick conductor fixed and changing the magnetic field with an AC current, alternating current, which is generally drawn in case of a transformer. Now, what is the cause actually of this eddy current? If you see to the picture, due to changing magnetic flux, induced current is set up within the cross section of the thick conductor, which is in circular manner, and it is in accordance to Lenz's law. It is the cross sectional manner. It is because the conductor has to be very thick one. And what is the characteristics of this eddy current? If you see that this eddy current produced in a cross-sectional manner and its direction is in accordance to Lenz's law, such that it opposes the very change in magnetic flux. That is, it opposes the motion. If it is the magnet you are allowing to move, then it opposes that one. And this eddy current causes a damping, huge damping, as you can have experiment in case of a bar magnet suspended in an oscillating bar magnet. Of course, when in presence of a magnetic field, then the oscillation quickly dies away. This is because of the damping presence due to the eddy current. And this damping causes equivalent work that appears as heat on the thick conductor. And this heat sometimes termed as iron loss or copper loss in the armature coil, and it can be minimized. This heating can be minimized by making of the armature with soft iron and with a large number of laminated core which are insulated from each other. Iron or copper loss, it is depending upon the material, whether it is made up of iron or copper. And why soft iron? It is because soft iron will have a low hysteresis loss, which will be discussed in our subsequent discussions. So therefore, this soft iron has a low hysteresis loss. And while laminated, if you see to the picture, if you make it laminated, the interface regions of the laminated interface regions will have opposite eddy currents, which are induced. That induced eddy currents are opposite in direction. One is up and another is down, and therefore the effective losses will be minimized. One will cancelize in each of the interface, they will cancelize, and finally the extreme components will be present. That is how the eddy current can be minimized by making laminated. And the application of this eddy current as huge, it is because you see to the electromagnetic damping. That is one case of application of this eddy current. And we use in laboratory also by making the deadbeat galvanometers, because the moving coil galvanometer, if you are allowing it to move, it will long time it will take to come to rest. So therefore, we make it deadbeat type by allowing damping in the galvanometers. Another application you can see also the eddy heat, the eddy current giving rise to heat, we use in induction furnace. In induction furnace, we use for heating purpose. In induction motor, which we are using in domestic fan also, we are using this eddy current concepts. And the electromagnetic brakes frequently used in trains, we use these eddy current concepts. And in speedometer and energy meters, where we use for fuel recording or energy consumption purpose, we also use the eddy current applications. Now, to make you more clear, make you some three-dimensional visibility of these ones, by some demonstrations. You can imagine this as the thick conductors, and here this is the thick conductors, and if you pick up this one thumb as the north pole and my forefinger as the south pole, now I can allow you that this magnet, I mean this within the fixed magnet, my magnet is now fixed. Now I am allowing this thick conductor to oscillate. So in that case, the direction which I have shown, that is the direction of the eddy currents along this case. I mean throughout this cross section of these eddy currents will be developed, and I can show you in laminated sections also that if you see, these are some of the laminates which I have joined. Each of them are insulated. You can see each of these are insulated. Now what happens, if you see it very carefully, this is the direction of the eddy currents. The direction, you can see that the eddy current direction is like this way. And when you make the transformer by laminated cores, each of the components, if I take away one of it, you see that each of the component at the interface will cancelize. So at the interface, I have given colors here to descendant. In the interface at these regions, interface means at these regions, the components are cancelling each other. So therefore, if I join along these cross sections, and this is the, of course, the thick one, this is the thick one, along these sections, the eddy currents cancels out due to each of these thin sheets, and therefore finally the last two extreme components will be there in the transformers. And this is how the concept of eddy current, which is one of the important application of Faraday's law, we will discuss more about electromagnetic inductions in our subsequent class. Thank you.